This corresponds to the second part of special respirations, in particular hyperbaric environments. Before we kind of look at hyperbaric environment and some negative consequences of being a hyperbaric environment, I want to discuss just the physiologic effects of just water pressure itself. So here we have a person who's standing neck deep in water. So we haven't put our head underwater. So what's the effects of just the water pressure on the cardiovascular system and the respiratory system? So what you'll notice is because of the weight of the water down here at the legs, it compresses arteries and veins in the lower body, which result in an increase in venous return. So you have an increase in venous return, you will have an increase in heart rate and stroke volume because of atrial stretch, the Bainbridge reflex. Stroke volume increases because of the Frank-Starling mechanism. Both of those, a heart rate increase and a stroke volume increase, will result in an increase in cardiac output. Because of the equation for mean arterial pressure, you will also therefore have an increase in mean arterial pressure, since mean arterial pressure is equal to cardiac output times total peripheral resistance. Well, what would happen as a result of that increase in mean arterial pressure? Well, that can result in an increase in urine output, because we had discussed the effects of mean arterial pressure on urine output in control of blood pressure. An increase in mean arterial pressure would result in pressure diuresis. So urine output goes up. You also will get an increase in breathing rate in someone standing neck deep in water. What happens is that weight of the water, it presses against the thorax, and it requires that person to expend a little bit more energy to breathe in, so their breathing becomes a little bit more shallow, and a result of that, breathing rate will increase to compensate for it. So here's just some of the physiologic effects of just standing neck deep in water. Well, what would be the effects if I actually dive, do say a breath holding dive, and go below the surface? So you'll notice this graph shows a relationship of depth below the surface of the water to pressure and also air volume. So one thing just to remind you about Boyles Law over here. Boyles Law says the pressure is equal to 1 over volume. So if someone dives below the surface, what will happen is because the pressure of the water on that person's thorax, the air compartments also will be compressed. And what would happen is, as a compression of those compartments, the pressure increases. And so what's going to happen is we're going to notice is absolute pressure increases the further and further you dive. So what you'll notice here at sea level, your absolute pressure, barometric pressure, is 760 millimeters of mercury. That corresponds to 1 atmosphere. So we can say it's 1 atmosphere. Here's the partial pressure of oxygen and nitrogen in the air that you breathe. And what you'll notice is, as I go 33 feet below the surface, the absolute pressure increases. It actually doubles. So why has it doubled? Well, standing at sea level, the column of the air extending from your feet upward into the atmosphere, it exerts a pressure of 1 atmosphere. Now when you go under the water, you got the weight of the air on top of the water plus the weight of the water itself. And it so happens that every 33 feet that you descend, you increase pressure by 1 atmosphere. And it's linear. So you'll notice 760 to 1520, that's doubled. Here you add another one on, another 760, you're at 2280. So the 33 feet is a magic number. So every 33 feet below the surface, you'll have an increase in pressure of 1 atmosphere. And 1 atmosphere corresponds to 760 millimeters of mercury. So what's the big deal? Well, because of Dalton's law, if I'm breathing compressed air, which is 21% oxygen, almost 79% nitrogen, what you'll notice is here is my absolute pressure. If you take about 21% of that, you'll get this for the partial pressure of oxygen. If you take about approximately 79% of that, you'll get 1,200 millimeters of mercury for nitrogen. And it steadily increases the further and further you go below the surface. So what we're going to be looking at is the effects of, what could be the effects of too high levels of oxygen, effects of too high levels of nitrogen, and perhaps also the effects of too much carbon dioxide. So what we're going to be noticing is as depth increases, the partial pressure of the gases increase. The partial pressure of these gases increases, you're going to force more oxygen, more nitrogen into the blood. So even nitrogen, which is not very soluble, with the high partial pressures that you see, you're going to force more and more of this into the blood from the alveoli. And so we're going to be looking at some of the effects of too much of these gases in the blood. So the first one is, what would be the effects of too much nitrogen? Well, because nitrogen is poorly soluble, it's usually not an issue when you're hanging out at sea level. But when you dive and the partial pressures of that gas get significantly higher, what's going to happen is you can end up with nitrogen narcosis. And the idea is, they call it raptures of the deep. The nitrogen will have narcotic effects. So what happens is the nitrogen dissolves very readily in fat. And what it'll do eventually, it'll equilibrate into the blood and eventually into the adipocytes, and also in lipid membranes. What it'll do is it'll have effects just like narcotics. It reduces ion conduction of membranes, affects neuronal excitability, very similar to how narcotics have their effects. So they compare some of the effects as being intoxicated. It's like having alcohol intoxication. About 150 to 200 feet, some people can get drowsy. As they descend even further, their strength diminishes, they get clumsy, they have poor judgment, their motor function, mental function can be a problem, can lead to convulsions and death. But thing is, this nitrogen narcosis can occur in shallow dives if a person stays down too long. So the big issue is when someone's diving, it's not just depth, it's time. So if the lower you dive, or the greater the descent, the shorter amount of time you can spend down there. If you have a shallow dive, you can still have effects if you're there for too long a period of time. So they have limits for depths if you're breathing compressed air because of the high levels of nitrogen that can result from it. Those people who have to do deeper dives for certain periods of time, they will do mixtures. They call them heliox mixtures, which is more helium, low level of oxygen. At least, well, it's only 10 or 5% oxygen. Remember, when you're doing those dives, even though 5% oxygen, you're going to still get a pretty good amount of oxygen in that person's blood. What they've done is they replace the nitrogen with helium. And the reason why they'll replace nitrogen with helium is helium has about half the narcotic effect of nitrogen. About half the volume of helium will dissolve in body tissues as nitrogen. And it has a relatively low density. It's like a seventh of nitrogen. So it keeps airway resistance to a minimum too. So why doesn't everybody breathe heliox mixtures? It's costly. So this is designed for people who are doing pretty deep dives or are going to be diving for long periods of time. The effects of oxygen, high partial pressures of oxygen, you can get oxygen toxicity. The high levels of oxygen will increase the amount of oxygen dissolved. What can happen is the high levels of oxygen can cause oxygen toxicity. It can lead to generation of oxygen-derived free radicals. The issue is that you can have things where it can cause damage of the respiratory membrane. It can have damage to a lot of different organ systems, affects a lot of different cells in the central nervous system. Usually, under most instances, hemoglobin buffers, acts like an oxygen buffer. It keeps tissue oxygen levels at a relatively safe range. But if the partial pressure of oxygen gets too high, more of it will be in that physically dissolved in plasma, which can generate, more likely to generate free radicals and lead to problems. Usually the acute oxygen poisoning is if you have exposures to oxygen levels about 4 atmospheres. If you're exposed to 4 atmospheres of oxygen, you can't be there for very long, 30-60 minutes, and you'll start having problems. Chronic oxygen poisoning generally doesn't have as many effects on body systems except for the lungs, because chronic oxygen poisoning is where the partial pressure of oxygen is only about 1 atmosphere, but because it's there for a long period of time, it can damage the epithelium of the airways, and also lead to inflammation of the alveoli, cause problems with the smooth muscle of the bronchioles, and can lead to pulmonary edema. Why relatively low levels of oxygen compared to like 4 atmospheres? If you have 1 atmosphere of oxygen, the reason why that will pretty much have just effects on the lungs is, and the other tissues be safe, is the other tissues are safe because of the buffering effect of hemoglobin, but the lungs are exposed to that directly to the higher oxygen levels. So oxygen toxicity, too much oxygen can lead to oxidation of polyunsaturated fatty acids, which are components of your cell membranes. It can also damage a lot of enzymes involved in energy metabolism. With the lower levels of oxygen, it's mainly problems on the lungs. The higher levels of oxygen, or the atmospheric levels of oxygen, will have effects on multiple organ systems. The toxicity of CO2 is generally not usually a problem with diving because of if you use proper gear, CO2 is going to be released out into the environment, and if you have improper functioning gear, yes, CO2 levels can build up in that gear. We can usually tolerate up to certain levels of CO2 because we compensate with our respiratory system. So generally where you see this is mainly a problem if someone has a malfunctioning gear. So generally carbon dioxide toxicity is not generally a problem. So we don't really worry about that as much. What would happen overall, though, if it does happen, is the respiratory center, as a result of high CO2, will be depressed. You get lethargic. You can also have narcotic effects and anesthesias. They kind of can't feel things as much. Now, kind of a rule of diving is you have problems with the high levels of oxygen, nitrogen at the actual depths, but you also have problems as you ascend. So we have to discuss decompression of the diver. And this is kind of a general idea, or kind of like a rule of thumb that divers use, that if they know their depth in meters and their time in minutes, if it's less than 50, they don't generally need to decompress. But other than that, they will have to decompress. So the decompression sickness was actually first described by a scientist who happened to be the scientist who showed you the relationship between pressures and volume. And I wonder who that scientist was. Who's the one that showed you a relationship between pressure and volume? See if you can answer that. Now, he first described decompression sickness when he placed a snake, a viper, in a vessel, and he increased the pressure. So he was mimicking having this snake being at a deep depth. Then what he did is he mimicked coming up or ascending from that depth very quickly. So he decreased the pressure, and as he decreased the pressure, he saw a bubble formed in the eye of the snake. And as a result, I mean, he didn't notice the bubble right away, is that the snake was in a lot of pain. It was writhing in pain. As he was looking at the snake, he saw a bubble forming in the eye of the snake. So, I wonder what was creating that bubble and creating this excruciating pain in this poor snake. Well, this poor snake had decompression sickness. So, decompression sickness, that you see in your notes, has a lot of different names. It's called the bends. You'll see that with problems in like your joints. It can be called Kayes-Wandover's disease, diver's paralysis, because it could cause paralysis. Dysbarism. It has a lot of different names depending on what its effects are. So you have a listing of different things in your notes. The effect of decompression sickness is from a too rapid ascent, and it's the effects of nitrogen coming out of solution and bubbling too quickly into body fluids. So if a diver has been down long enough or deep enough, he or she will have a significant amount of nitrogen in their lipids. Now, if they come to the surface too quickly, the nitrogen bubbles will develop in body fluids, either intracellularly or extracellular, like your tissues or your blood. It can cause anywhere from minor to serious damage depending on the size and the number of the bubbles, which can appear for many minutes to hours. Everybody's going to have some nitrogen bubbling up, but if you go too quickly, the bubble's going to be too much, and the size will be too much, and it can cause a lot of different problems. Where you get the bends, this is where you can get gas bubbles in blood vessels, which then cause tissue ischemia, and worst case scenarios, tissue death. You can get pains in the joints and the muscles of the arms and legs. Most people, about 85 to 90% of decompression sickness is the bends, where you get the pains in the joints and the muscles. Some people can have nervous system symptoms, including being dizzy, to being paralyzed, or becoming unconscious. The paralysis can be temporary or be permanent. They'll get things like pins and needles, feelings, weakness, loss of sensation, and also a small percentage of people get what they call the chokes, in which you get massive numbers of these bubbles of nitrogen coming out of solution in the capillaries of the lungs, which causes shortness of breath. So with decompression sickness, again, it's because of these development of these nitrogen bubbles in these body fluids from ascending too quickly from a dive. Now, there are decompression tables available to people that dive. They tell, depending on how long or how deep they were diving, how far they need to ascend and then stay there for a little bit of time, and then slowly ascend and eventually get up to sea level. Now, decompression sickness may not be immediate. Someone could get off from their dive, get on a plane, and so many hours later get decompression sickness, and that has happened, where someone went diving, they came up, they were on a plane going back home, and they got significant decompression sickness. They had to land the plane, get the person off the plane, and start doing some, put them in a hyperbaric chamber to kind of mimic the environment they were in, and then slowly decompress them. Now, if someone needs to be ascend too quickly because of something happened, some malfunction of the equipment, they need to ascend too quickly, they'll get them up quickly, then put them in a hyperbaric chamber. You can also, if someone needs to be dive very deep depth, or for long periods of time, we need to be down there for a long period of time, is they will use things again like heliox mixture instead of they may use special chambers where these people live, which kind of mimic this high environment, so they don't need to decompress. So these are people who are commercial divers and need to work on like offshore oil rigs, or Navy divers that need to be down for long periods of time. They actually live in these different types of saturation chambers. And in class, I'll give you my story about some of these early decompression chambers, not really decompression chambers, these saturation chambers where people can live while they're diving for long periods of time. Now, another thing that can happen from an ascent or even descent is barotrauma. Barotrauma is a result of changes in the volume of air in spaces as the body increases or decreases pressure. And the pain is related to gas in body cavities. So some people who are divers, if they've used certain dry suits, there are certain dry suits where you can inject air into the suit or vent air out of the suit. The air is injected in the suit when they're descending. It's vented on the ascent, because what can happen is that little bit of space between the suit and the person's body, that represents like a cavity, body cavity. And because the effects of changes in pressure, you can get like the suit can kind of pinch that person, so they can change the vent air or put air in to prevent that from happening. But where you can have issues is, one of the things is pulmonary barotrauma, where you have if they come up and they hold their breath on the ascent, the compressed air in their lungs expands as the pressure declines. As you're ascending, the air pressure is going to decline, and they can cause the lungs to overexpand and rupture. So they have to remember to make sure they let air out of the lungs, otherwise the compressed air is going to cause the lungs to rupture, expand and rupture. The other things that people may notice because of changes in pressure is if you're diving, it can cause problems with like the little bit of pockets in your teeth, and people have problems with like real painful teeth when they're diving, or the ear can have problems too, because the air is held in air spaces other than the airways, and if those cavities can't equilibrate readily with external pressure, the increases in pressure, say on the descent, can distort the cavity wall, which can result in like pain or damage. So for example, if someone's eustachian tube is blocked, the middle ear pressure can't equilibrate with external pressure, and the tympanic membrane can rupture. So barotrauma is a result of changes in the volume of the air in these spaces in the body as a result of changes in this absolute pressure. So this will be the end of this lecture, and anything that I didn't cover in this webinar, I will make sure I cover in actual lecture itself.